Welcome everyone, I'm Andy Beet. I'm part of the Northeast Fisheries Science Centre Atlantis development team. We are currently a team of 2 developers, Joe Caracappa and Rob Gamble. We have a project manager, Scott Large, and one of my roles in the team is to help create tools that aid in the running of the model and analysing the output. So today we'll be talking a lot about tools, a lot about strategies and workflows relating to the development and the calibration of an Atlantis model. Do we have the right tools? Do we have a strategy? I don't know, do we? This is something I want to find out. What I do know is that Atlantis is a beast of a model, and with many parameters the development process can be a frustrating and painfully slow process, and we can attest to that. If you are unfortunate enough to be tackling this alone, then I can imagine this can get overwhelming. So my question is, can we as a community create some standards and strategies and guidelines to calibrate in Atlantis? So we have several goals for this presentation. Firstly, we want everyone to start thinking about their strategies for calibration. So how do you think about diagnosing issues with your model? Can you write down your thought process? Second, which set of tools do you use to help you diagnose these issues? Do you use readily available R packages? Do you use Shiny apps? Do you create your own scripts or borrow from others, or something entirely different? Thirdly, can we as a community create a calibration strategy guide, if you will, to aid all developers, current developers or future developers? Something like Appendix A in the Atlantis manual, something in that flavour. So whether this is on a GitHub site or part of a current Confluence site or something entirely different, I'm hoping we can, but I'd like your opinion. So after 18 months of developing the Northeast US model, we would have definitely benefited from some kind of document like this. If it existed, maybe we could have shortened our time frame. So there's going to be a collaborative document available during the summit for people to edit as they see fit. We ask that you do try to contribute to the content. It would be greatly helpful to everybody. So what information do we already have to us in the literature? Of course, the Atlantis Confluence site, excellent resource, and that should be the first stop for anybody. Then, that I'm aware of, there are only 2 publications that talk about the kinds of problems that I want to talk about today. If there are any others, please feel free to enter these in the document. The first being the paper by Kaplan and Marshall. While this paper is mostly aimed at a person who would review an already calibrated model, it contains content that we have incorporated into our development process. The general model requirements are: all groups should persist above some level, 10% of initial biomass is considered, all groups should reach some equilibrium state in an unfished system, all groups should reflect historic trends, and temporal variability should be replicated. However, this tends to be only possible if you're forcing a model with recruitment data. Also, realistic overall system productivity should match stock assessments or life history theory within some tolerance level. Natural mortality should decrease with age, and age and length structures should match what is expected. And finally, diets, they should be taken from empirical studies. Now, if all of these make up a general set of requirements, do we have a strategy to achieve these, or even the tools to determine if the model possesses these qualities? The second publication of note is that of Pethybridge, I hope I pronounced the name right, and and she mentions a three-phased approach to development. And she talks about phase 1, where in the absence of phishing, persistence and stability of all groups should be seen. Then phase 2, once you've reached phase 1. Phase 2, include constant phishing and then determine if realistic responses to phishing occur. When that passes, phase 3, add historical phishing and environmental drivers to reproduce historical trends. While this sounds simple in principle, in practice it's far from it. The paper outlines a lot of great tips on how to approach certain development issues, like the flowchart you see on the right here. This maps out a sequence in which the parameters should be checked if groups are declining or increasing rapidly. So what does the calibration process actually look like, at least to us in the Northeast Fisheries Science Centre? So we can represent this process by this flowchart on the right here. So the model is run. Issues are then identified using a set of available tools and a set of defined criteria. Once these issues have been identified, then they need to be prioritized. So a strategy for determining the cause of the problem needs to be employed. This often comes from experience or the use of exploratory tools or reaching out to others with more experience than us. Then parameter changes are implemented. The model is run with the updated set of parameter values. This can either be a single model run, or as we do, a collection of runs exploring a gamut of parameters to address multiple issues simultaneously. At this point, the cycle repeats, and often you find a step forward can set you 2 steps back. So this calibration process for the Northeast model is still ongoing. We've been working on it now for about 12 to 18 months, depending on how you define the start. So really, each compartment in this flowchart is by itself a complex set of decisions. So we've briefly discussed some of the criteria earlier mentioned in the Kaplan paper. However, at this stage in the process, we need to define them for model success. So how we're defining persistence, how we're defining stability, what about the distribution for age, reasonability. This actually is a criterion that we've defined. It's one where the overall biomass of a group lies within reasonable bounds based on data or otherwise over some defined time period. Other criteria might be whether you have maximum weight length criterion satisfied. Maybe you employ some skill assessment metrics like those in the Olson paper. Maybe there are other criteria. What do you employ? So how do you actually determine if the model has met certain criteria? It's reliant on tools available to process this output, maybe visually or maybe using functions that pass or fail. So what are we all using? Well, the tools that are out there are the Atlantis tools package. It's an R package. It makes it really easy to read in Atlantis output for your own code use, and there are some plotting functions employed also. Then there is the Reactive Atlantis. It's a Shiny app focusing on visual aids, helping with calibration and troubleshooting. There's another Shiny app called Shiny R Atlantis, which I must admit I'm not that familiar with. And it's meant to aid in visualizing parameter files. Now, all of these products I just mentioned, they're all available on the Atlantis Ecosystem Model GitHub page. I recommend you check them out if you don't know about them already. I'm sure most of you do. Now, many of us also use our own code that we've cobbled together, and possibly snippets of code that we've borrowed from others. So the question is this set of tools enough? Do we need other tools developed? And on this point, does anyone else have tools that they're currently developing that might benefit the community? So then we're on to prioritization. So which issues that you've identified should you focus on first? I mean, it seems sensible to focus on bottom up. It seems sensible to rank species based on importance. Also seems sensible to focus on species that have data. How does everyone else prioritize? And how do you prioritize calibrating a group when you have no data or insufficient data? How do you even calibrate at all under those circumstances? So then, once you've prioritized your issues, you end up having to come up with a strategy for solving these issues. And hopefully the tools used to identify the issue in the first place do shed some light on what the issue might be, but maybe it doesn't. So how do you go about trying to figure out what has caused a particular behavior? Again, the Pethy-Bridge paper has some good tips on how to do this, but it wasn't and isn't intended to be exhaustive. So how do we do this, and what is a good strategy? We employ a few different strategies. The most common one is we try to replicate a known phenomenon. For example, take age structure. We noticed that the age structure of cod in our model was biased towards very large individuals. You'll see an example of this later. And this isn't what we know is happening to cod. So, we map out the parameters related to the age-based process, like growth, maturity, diet, fishing, etc. And then we blindly, maybe not blindly, but we change the parameters in a direction, and then we get to see if we're on the right path. This is quite common. Then a second strategy, not really a strategy, is we just experiment with the parameter values with no real knowledge of what a reasonable choice is. We review the model's response, and then we change the parameters accordingly in a particular direction. So, for example, the documentation says that linear mortality should be low. But I mean, how low is low? Is it 0.01? Is it 0.0001? We found 10 to the minus 13 worked for us. But is that too low? We don't have much of a concept for that. So really it's a strategy where we have no grounding to true values. Another strategy is a data-driven strategy, where basically the end justifies the means. So we don't really care. For example, we don't really care what the growth rate is if the output looks good. Are there any other ways that anyone else strategizes? Now, for poor data systems, you might not know a great deal, so you might focus more on the biophysical processes and just let everything else fall out. I don't know. We'll go through a few examples of how we approach some of the problems, but we'd really like to know how others tackle these problems also. So eventually we get to a point where we say calibration is done. But when is that? We've probably all got our own set of done criteria. Maybe we should think as a group about setting some standards based on what the model is to be used for. Should we be including a sensitivity analysis prior to saying done? Phase 2, described by Pethy-Bridge's paper, is a sensitivity analysis of sorts, where it focuses on the response to the model by imposing constant fishing pressure to calibrate unfished model. But should we be testing the sensitivity of our calibrated models prior to their use in management strategy evaluation to make sure they do respond in expected ways? So let's take a sidestep and briefly talk about the Northeast model, go through a few runs of the calibration process just to get some context. So we're currently calibrating version 2.0 of the Atlantis model. Joe Caracappa will be talking in more detail about the current model and its differences from version 1 in another presentation later this week. I'll leave that to him to expand. But briefly, we have 30 polygons, 22 of which are dynamic. There are 89 functional groups made up of 54 species, 5 mammals, 4 age-structured invertebrates, 3 zooplankton, 3 phytoplankton, and 11 macroinvertebrates. The model is forced from the bottom up with primary production and physics, and catch is also forced. The model takes about 12 hours to run, which means we often run it overnight. We have the entire parameterized Atlantis model on GitHub. The model gets versioned according to semantic versioning rules. All the data and the R code used in the calibration criteria are also on GitHub. So in theory, anyone that has Atlantis installed on their machine should be able to clone the repo and run the model, in theory. So, a little about our workflow. It isn't perfect and it's still a work in progress. We have a project board in which we add tasks that need to be addressed. These can be tasks like compiling data from assessments, figuring out why herring is crashing in the model, write code to test for a persistence criterion. Members of the team then assign themselves to these tasks. The team meets daily for 15 minutes or so to discuss progress made the previous day and then what their plans are for the current day. We use GitHub extensively in our calibration. I'm not going to go into the details of the flowchart on the right, but if anyone is interested, you can ask about that in the questions section, and I'll go over that. However, we do consider GitHub to be one of our tools in our belt. Extremely valuable. So our team works exclusively on Windows machines. So we can't compile Atlantis locally, not the latest version anyway. And due to security restrictions at our center, we can no longer use Docker either. So instead, our only option is to use Podman on our internal servers. Now, there are very minor differences between Podman and Docker. It's easily transferable if you're used to using Docker. The benefits of using containers is that we can run multiple instances of the model at any one time, obviously dependent on the number of cores available. Now, this has increased the speed in which we can diagnose viable parameter values. So we currently have 4 criteria in which we're trying to satisfy. We've called them persistence, stability, reasonability, and biomass at age structure. We're going to take a quick look at those now with some use cases. So let's go over persistence. We define this pretty much straight out of Kaplan and Marshall paper. All species and groups must not go below 10% of the initial biomass within a set period of time. We use the last 40 years of the model run as our time interval. So we've developed several functions to evaluate these 4 criteria. And the output from the persistence function is shown on this slide. The final column is the main column you want to look at. That indicates whether this species code has passed or failed the criterion. So the output displays species and their species code in Atlantis, the initial biomass of that species, the minimum biomass reached in the run, the time at which that minimum was reached. T1 and Tn are the first and last time points that persistence was not met, and then of course an overall pass or a fail. So this function, the beauty of this function is that it's very quick to run. it only relies on two files, the biomass, biome index text file and the functional group CSV file. And because it runs fast, we can prioritize pretty quickly which species we want to focus on and fix for the next model run. So in this instance, let's take winter flounder since it fails the persistence criterion, and let's delve a little deeper. So why does winter flounder collapse? So these figures that are on this slide are all pulled from a suite of plots that are made in what we call our post-processing step. For all of the plots that you're going to see moving forward, pink represents the largest size class and orange is the smallest, and the color grades from orange to pink. So in this first figure here, why is biomass declining? We can see that it's declining and pretty much hits zero about halfway through the run. So in conjunction, we see that the fishing mortality spikes around that time, but it's also minimal in the years prior, in which biomass is declining. And in addition to this, you'll also see that the predation mortality swamps fishing mortality anyway, so the fishing mortality is negligible relative to predation mortality. What is curious is the biomass at age. So it appears like there's an age class that's growing up and then dying out, and it looks like there are no recruits being replenished. The next plot, this average weight plot, this just shows us what the average weight of an individual is in each size class, and you would expect this to increase through our age class, and we see that, so that looks normal. So what it appears to be the issue is a recruitment issue. So what we did through somewhat trial and error is change the parameters of the Beverton-Holt relationship that we have coded, and that is the resulting time series that comes out of the change. Looks a lot better. So the next criterion is the distribution of biomass by age. Now in an unfished system you might expect a lot of big fish. In fact, the majority of the biomass would be the larger size classes. However, in a fish system, and especially in one in the northeast, you would not expect this. So this function returns the age class containing the most biomass. So if an age class is either 1, which are the recruits, or 10, the species group fails this test, meaning that all the biomass is in one of the end age classes. So effort is then put towards shifting biomass at age away from these boundary age classes. The function also returns the priority of the species group and also the level of fishing effort imposed on it in the model. This also gives us an idea of how we want to prioritize the species that fail this test. So being as Pollock is top of the list there and fails, let's have a quick look at that. So let's try and diagnose this. When we look at the overall biomass, everything seems okay. It looks persisting, it looks pretty stable. But when we look at the biomass at age, it confirms that what we got from the diagnostic routine, that the largest size class is dominating the biomass. To combat this, all we did is we changed the growth, the mum parameter, the whole distribution over the age classes. We found that it was in a linear form, meaning the mum parameter increased as you went from the smallest age class to the largest, So we changed that to more of a dome shaped, so the larger size classes had lower values and the highest values were in the middle age classes. You can see from the third plot there that the largest size classes have been reduced significantly, and we get more of an age structure that we would like to see in the model. The next criterion would be stability. Now, we've defined stability as a rate of change that's less than about 5% over the last 20 years of the model run. And we selected this value of 5% after analysing a selection of assessed stocks for which we have data. So in this function, we fit a linear model to the last 20 years of the biomass data. We calculate a relative change, and then any value that exceeds 0.05 indicates a failure of the stability criterion. And we can see here black sea bass, its relative change is 8%. So let's focus on that and let's look at some of those plots. Alright, so we can see that biomass is increasing. We know that anyway from what we just talked about. The biomass at age also shows this pattern. Growth also shows that it is increasing. Consumption also, that probably explains the growth. So while the solution doesn't at first sight look too different from the initial biomass, if you look at the Y scale, it's greatly condensed, and hence the trajectory is actually a lot flatter than it was before. And even the last few years of this time series looks like it might be flattening out. So to get to this point, again, it was a clearance rate reduction to reduce the amount of volume of water that this species searches. And then we fine-tuned the growth, the mum parameter, across all ages. This seemed to fix this problem. So the final criterion we have termed reasonability, and this one has proved to be the most problematic after initially thinking this would be the simplest. So the criterion is, does the biomass time series over the last 20 years of the model lie within reasonable bounds? So what are these bounds? Well, the data that are used to form these bounds are a combination of stock assessment estimates, state survey estimates, or in-house calculated swept area biomass estimates from bottom trawl surveys. And the bounds on these estimates are measures of spread, estimated measures of spread from this data. So for species without data, they're based on proportions of the initial biomass. Currently, I think we use values of 0.2 initial biomass and 2 times initial biomass as our bounds. But we just made those up. We don't really have any idea, and we don't really know what the best values would be or how to even work out what the best values would be. So this function here, we get a pass or a fail, like all the other functions, and if you look at the last column, you'll be able to determine if this pass or fail was based on actual data or initial biomass values. We do find that if a species tends to fail this test, it's usually because the species is too abundant rather than not abundant at all. So let's focus on. So as we can see from the slide, cod is persisting at high levels. and we can see that this is mostly due to an overabundance of age class 2s in the model. The weighted age looks fine. We have an increasing weight with age class falling within bounds that are acceptable. However, consumption does look a little strange. So the solution to this is pretty obvious. We needed to reduce the age class 2 biomass, and we do that by reducing the clearance rate and the mum value for age class 2s. And the result is that fifth plot where we can see, even though age class 2 is still the most abundant, that is expected, it's what we want. We see real values of cod age class 2 being one of the most common age classes, so this seems okay. The order of magnitude of overall biomass has been reduced by about an order of magnitude. It's still not entirely, it's not low enough to pass the reasonability test yet, but it's in the right direction. Reasonability is still a work in progress, mostly because we don't have the right data to be testing this against right now. And I know in a very data rich part of the country. So hopefully you could have identified with some of those examples. Hopefully you can provide some examples of your own. We'll have a collaborative document available during and after the live presentation, which I hope you'll all contribute to. So here's the opening slide again to remind you of the goals of this presentation. Hopefully it's made you think about how you go about calibration, and which tools you have available and which ones you use, and potentially which tools you'd like to have in your arsenal to answer some of the questions you have that you can't currently answer. And then hopefully you have an opinion on whether creating some global strategy guide for the community at large is a worthwhile endeavour. All of these I would like to know about. Thank you. Last slide. Before we get to questions for me, I have a whole bunch of questions for everybody else. So I want to know what your calibration strategies are and how you prioritize going about finding solutions for problems in your model, and how are they different from what we've talked about here today. Do you have all the tools and all the data available to achieve your goals? If you do, that's fantastic. I'd like you to expand on the tools you have that you like and you use and you think everyone would benefit from knowing about. If you don't have the tools that you need, what is it you need? What would you like to do? What are you trying to find out in your model? Because I'm sure everyone else would like to know that too, and they don't have those tools. And then, does the model's proposed use affect how we go about calibrating our model? So basically, do we need different tools or a different set of criteria based on the model's use? And then the last question I want you guys to think about is, can we identify shortcomings ahead of time? So, for example, how can we satisfy the criteria that we set for our model if we don't have any data? Can we do something like filtering the model output to meet stock assessment data if we only have assessment data for so many ages? Any other shortcomings that we can think of ahead of time that we can maybe address before we get to that point where we are so into calibration that we go, oh, didn't think about that. And on that note, I am going to allow you all to ask questions and hopefully calibrate hopefully collaborate and enter answers to some of these questions in the link to the documentation. Thank you.